Our next speaker is Dr. Hugh Deasy. He's a theoretical physicist, formerly based in TCD and Dunsink Observatory. He's worked for 3 decades in aerospace, namely at the European Space Operations Center, EOC of ESA. There, he was a flight dynamics and simulations person. He developed programs to control the orbit and attitude of satellites in LEOP and routine operations in the phases of their missions. He was also on the launch team for numerous satellites. So in the last few years, he has concentrated on developing inventions which include Lorentz force propulsion and also inertial propulsion and energy generation, along with FTL communications and propulsion. He's going to be speaking today on the Deasy-Lorentz system for EM propulsion. So everyone, I would like you to welcome Dr. Hugh Deasy to the call. Hugh, let me ask you to unmute and I will hand things over to you, sir.
Thanks. Okay, so just sharing my screen here. Can you see that?
Yes, no, it looks beautiful. It's perfect. And your sound is great. Your video is good.
I'm afraid it doesn't look as sexy as Eamonn's presentation, but anyway, it's maybe stronger in physics, whatever. And that's the Deasy-Lorentz system, which I claim is high performing. And for some introduction background, as you mentioned, I'm a physicist and astronomer. For those interested in astronomy, I was into Cepheid variable stars and mass loss and period changes of them and all that. That was my PhD, as it were, an MSc. And after that, I went on to 29 years at ESOC, which is the Houston of ESA. And I was controlling orbit attitude, writing programs, being on launch teams, and also with mission planning. And that involved also launch window planning for various launches, finding the windows in the year that you could launch the satellite, etc. Anyway, since essentially 2000, I began to get interested in alternative methods of energy and propulsion. And I was essentially adding skills because I was coming from a theoretical background, and I found I needed to make these prototypes. And so I had to sort of dirty my hands with engineering to get into making the prototypes. But some of the prototypes were so complex, I had to farm them out to engineers who would make them for me. And that's the case with one of my systems at the moment. But for the Lorentz, I could make the simple ones, but for the high current tests, which were the key thing in this field, I had to go to specialists in the field. Well, okay, the vision, it's not really one of reactionless propulsion, but the prior art, let's say, was more in that direction, because I claim my system is more one of nonlinear reaction. Newton was only familiar with things knocking off each other linearly, the old mechanical knockaroo. But in electromagnetics, you have nonlinear effects. And good old Newton wasn't really familiar with that. So his third law didn't take that into account. So you can say we have a reaction, but it's not a nonlinear reaction. And just looking back at some of the prior art, Norman Dean in the 50s was famous for his inertial propulsion. Joseph Campbell was the editor of a famous science fiction magazine. He was given a demo of Dean's system, one of the few who were privileged to actually see it in action. And what the upshot of that was that Joseph Campbell was determined to promote him and had him on the cover of his magazine, etc. And Unfortunately, though, then came, he didn't really get investors, and there was no internet in those days. But even with the internet, it's difficult to get investors. So I appreciate the difficulty he may have had. It may have been that he was onto nothing, but it looks like, for example, Stephen Hampton is now replicating his effect quite successfully. I've got another version of an inertial propulsor, but today I'm talking about my electromagnetic one, which has the advantage of being solid state, just like Roger Shawyer's EM drive was a solid state thing. It was essentially a sewn-off cone or frustrum into which he injected microwaves, and NASA and a group in China, etc., claimed to have replicated it, and probably did to some extent, although at the moment the state of play is that Martin Tajmar, a physicist who has investigated various propulsion systems, has essentially said that the micronewtons seen by these groups was an artifact of the heating of the system, something like that. But anyway, on to the nonlinear reaction propulsion with the Lorentz force. The Nassica's Lorentz thruster failed. That was backed with various crowdfunding, etc. But apparently, although it was meant to produce hundreds of newtons, produced just millinewtons, and probably that was just due to the Earth's magnetic field, as I've seen in some of my low current cases. Because low current cases, in my case, are the Earth's field is the bugbear of the experiments. But for the Nassica system, even though he was using superconducting, he was using it in the wrong way, and even the Earth's field was even interfering in that case, I believe. So this two other cases were Akbar Rahmani Rajad of Iran and Q Qiang of China, but my simulations had shown that similar setups to theirs simply didn't work. There are various rules of thumb. One thing is that, incidentally, okay, I'll go on to the theory and I'll show you that later. But to complete here, I claim that my system does work, and I'll show you why in a minute. So the mission, why should the Lorentz force lead to anti-gravity, etc., and nonlinear propulsion? Well, with several independent simulation packages, all based on Maxwell's equations, if you see the same pattern occurring, that indicates that you have some solid physics behind you. That emboldens you to go on to the next phase, which is to set up a test system to test this out. And this is exactly these are exactly the steps I went through. So initially I went through the theory, and this is what I mean by nonlinear. For two wires here, I1 and I2, in Wikipedia on the Lorentz force, you find this equation, which is the meatiest equation we have here. And it shows a current element on I1 interacting with a current element on I2 multiplied by the distance between the two, the unit vector, and divided by the magnitude of the distance. And you can see here with the mu0 over 4 pi that one of these elements is producing a magnetic field interacting on the other elements, current. And this is the way you calculate the net effect. And anyway, what you find is that F12 is equal, but not exactly opposite to F21. So the the force on wire 1 due to wire 2 is effectively equal to the force of wire 2 and wire 1, but is only opposite through 90 degrees, non-linearly through 90 degrees. So this is the basis of our propulsion system. Again, if you probably are, most of you, familiar with these particle plots of particles interacting with a magnetic field into the board, where they go in spiral, either in circular paths or decreasing spirals if the field is very strong. You can see it here with the force and the velocity, and the magnetic field is perpendicular to both of those. So they form an orthogonal triad. And anyway, in my proprietary system, the forces can be unbalanced, leading to this non-linear reaction force, net force. By the way, I'm not going to show the details, the full details of my coil, because I realized that I essentially haven't patented this yet, and I won't patent it until I get some investor investing in the system. And that, at that point, I will light the fuse of the patent. But when you issue a patent, you're lighting a fuse, essentially, until your patent explodes on the world scene, and anybody can look into the details of your patent and make the system. However, I don't want to be like Dean and go to my grave without having implemented stuff. So I will actually give a limited disclosure here. And what you see here is something like my system. It's not actually how my system is. You have a magnet interacting with a current flowing in a wire, producing the force at right angles to both of them. And what I see in my system, although there are larger forces at intermediate points, I see this in my integrations over the whole system, you get large force, but then it all peters down to 10 to the minus 7 times I squared. And this is a good rule of thumb, because incidentally, the in going back to this slide here, we see that what you get from that integration is effectively if I1, I2 by the length of one of the wires multiplied by or divided by the length of the mean distance between them. And the mean distance is almost the same length as the length. And in fact, it's about half of it. So that's why you say it's about 2 times 10 to the minus 7. That comes out of the mu0, which is 10 to the minus 6. And then 4 pi knocks it down to 10 to the minus 7, et cetera, et cetera. And the railgun is a good proof of concept of the Lorentz force. That has essentially made the Lorentz force famous, at least in military circles. There are some military people are excited by the railgun, and the US Navy has developed that to a fine art, and they've actually shot projectiles out at unprecedented ranges. It really has a great range. And so you can shoot your projectile out and hit your target many kilometers away, because it is a very strong force. In this case, the projectile completes the circuit. You see there, the current is flowing in the rails here, going from the positive to the negative side of that. And the battery is in the background. Now, what Matthew Schroeder at the US Naval Labs did was he suspended the rails from a pendulum, and he had very sensitive force meters attached to it. And what he showed was that, well, obviously he had the plastic constraints on the rails to stop them being pushed apart, because they would repel each other apart and also be repelled by the projectile, which wouldn't be a very effective gun if you had it, if the projectile fell down because the rails shot apart. That wouldn't be very good. So obviously you have some constraint on the rails to prevent them from shooting apart. But what Matthew Schroeder showed was that that was it as far as reaction was concerned. It was purely lateral reaction, and there was no backward, there was no recoil in the gun, in other words. There was no recoil. So if you were holding that against your chin, you wouldn't get a nasty jolt because there'd be no recoil. The recoil is all in the battery. Anyway, the next phase after all that theory and prior art was looking at simulations of the system. Now, what we got here in FEM 4.2, many of you are probably familiar with FEM, Finite Element Mathematical Methods 4.2, two-dimensional electromagnetic simulation. It's stock and trade for the engineers and people working in fields like this, also for physicists. And what you find in my system, because of the asymmetries I employ, biomagnetic systems, etc., on the coil, you get this asymmetric parabola. Because if force is meant to be I 10 to the minus 7 times I squared, current squared, then you would expect to see a parabolic shape. But here you see the skewed parabola to the positive side. And then sometimes it's on the negative side because I have the devices are on the other side, whatever. And by the way, what I'm going to show here is now a 3D simulation. The 2D simulation actually confirmed this 10 to the minus 7 times current squared, at least on the left. That's almost exactly what it is. Whereas the three-dimensional simulations were a bit disappointing in that the force constant was 10 to the minus 9. And that means you have to pump in a lot more current to get a force, which is bad news. So anyway, I'll come back to that later during the high current test, which tested that out. And the third simulation that I employed was the Magnum electromagnetic simulation. And here I just show a symmetric coil. I don't show the devices. But incidentally, when you attach these devices to the coil, what I did initially was to have a setup that would work to send the coil in the plane of the coil, because the Earth's magnetic field can only cause a twisting motion and a swaying motion to and fro, but it can't in the face of the coil, but it can't move it in the plane of the coil. So that's why I initially had a setup for the to go in the plane of the coil. However, I'm not going to show the details here, but I can, in my more advanced system, which I only developed in the last 2 years, most of this, the stuff I'm talking about is from 10 years ago, but in the last 2 years, I developed a wrinkle on the system, which allows you to get, by the way, one kilowatt produces 1 Newton in the first version of my system, which is again is comparable to other systems. I'll show you that. Anyway, here again is that biased parabola. Again, now the bias is on the left because the devices were on the left. But you can see here that the Magnum simulation was very good in giving flux plots of the three-dimensional setup, especially when I added my devices to the coil. It was very good to get confirmation of the theory, what they should have done. And they, again, I showed them here in the first prototype. Now, the very first prototype I ever set up, I made a mistake in employing much too heavy material. I had much too heavy add-ons to the coil, and they were specially engineered, but they were much too heavy. If anyone knows engineers, this is my experience anyway, they tend to slap on metal and metal and metal, and until you get a very heavy prototype. It's very hard to convince an engineer to make a light prototype. And this is what I had to get them to do, was to produce a light version of what I had in 2012. It set me back an entire year until I realized I could use lighter materials and probably get the millinewtons I would see in this coil. I know millinewtons sounds boring, and it is in fact a very minor thing, although in fact it's 1,000 times better than Shawyer's thing with micronewtons. But still, you need to get confidence, to build up your confidence, you need initially to get millinewtons, then you can go on to thousands of newtons. And that's what I got from the high current thing. So that was incontrovertible. But here, what I really did in this coil was I corrected for the horizontal component of the Earth's magnetic field. And I've blotted out the attachments here, but the actual coil then would move to the left here due to these pulses. And what you find out is that you're making a pulse and it causes it to move in the plane of the coil. However, because I'm only correcting for the horizontal component of the Earth's magnetic field, I was still getting a swaying motion. So it was moving in a sort of an elongated ellipse. So this wasn't optimal. And the other point, I'll come to that in the next slide, but first of all, to point out that I was wedging the wire under the heavy devices here, like the battery charger and the car battery. By the way, the reason I needed a battery charger was after a while, after many hundreds of these tests, the car battery began to run down. And I needed to get a battery charger to keep the battery charged up. And these devices were nice and heavy and were good for wedging the wire underneath them. And that isolated the system mechanically. So a favorite test of mine before doing a test was to knock the wire down. If I was going to complete the circuit by touching the wire onto one of that electrode you see there, I would first knock it very strongly onto the plastic of the battery casing before I hit it onto the contact. And if this purely mechanical motion didn't cause any motion in the coil, then I knew that I'd isolated it mechanically. So these are all the factors that you have to consider: mechanical isolation, correcting Earth's magnetic field, and getting it to go for the Earth's magnetic field anyway. For the other as I'll show with the high current system, the Earth's magnetic field disappears because it's insignificant. But for these ones here, it turns out, coincidentally, the Earth's magnetic field produces the same dimension of force as you get from the Lorentz force. And that's why you get it moving as a compass needle moves to hit the magnetic north. And in the same way, because the coil is essentially a magnet, an electromagnet, it swivels to be in line with the Earth's magnetic field horizontal component. And because this was thin wire, I couldn't tilt it. Now, in the next slide, I'm going to show the tilting of the coil, which thick wire. You can, with this thick wire, which is 1.5 millimeters thick, you can twist the coil upwards so that it's pointing at the actual direction of the Earth's magnetic field with the horizontal and vertical components combined. By the way, here I've copied and pasted the right and the left, so I've eliminated the devices on the coil. And again, I'd set up the coil to go right to left rather than forward and back, because the forward and back could be confused with the vertical component of the Earth's magnetic field. And what I got here was indeed, I could show you a video, but I won't because I don't have time here. But and also would give away too much because you actually see the whole system. But what you see between these two stills of the video is that it's moved over about a ½ centimeter. And if you have, for an totally optimal setup, you can get up to 1 or 2 centimeter difference swaying action in this pendulum test. By the way, the pendulum test is always thought to be the ultimate test in showing that something is really reactionless. However, with the Earth's magnetic field, you always have the sneaking suspicion that something is there in the background. It's really the invisible hand moving the coil. But so that's why you have to go to the high current tests. And this was at a company, Hilo, near Karlsruhe in Germany, which was very kind in agreeing to allow me to use their surge current generators, because surge current generators are magnificent for this. About the only thing on the market which will shoot thousands of amps through the wire, even if it's only for 20 microseconds. But this thousands of amps produces thousands of newtons, and that's totally swamps what the Earth's field produces, which is only a few newtons. But anyway, sorry, I should go back here. This was a frame from a video of that test, and how they had set it up was that the surge current generator was in the lower rack of a rack, and at the top was this sample box with a perspex lid on top, so you could see into the coil and the system. And I've only shown a few of the attachments, but I've again cut and paste the left and the right here, and I've blotted out certain things. But you can see the supporting wire is a twisted wire, because in this thick wire coil I could only get in about 20 turns. Even one turn, if you have 10,000 amps going through it, even the lead wires could produce a high force of some sort and falsify the results. But the twisted wire of the going and returning current means that you have positive and negative current in that twisted pair, and that means that you cancel the magnetic field. So that's perfect. You have an isolated system then with this lead-in twisted pair powering it. And anyway, this was the first or the last frame in the coil before in the video before the pulse, this mighty pulse of 10,000 amps. By the way, we were using a surge current generator that could give a maximum of 30 kilowatts, 30,000 watts, 30,000 amps rather, 30,000 amps. Actually, it's a mega amp. It's 60 mega amps that it's producing. But what we have, but only for 20 microseconds, which means that you're only putting in a few watts in total, average over the second. But for that 20 microseconds, you're putting in megawatts. And anyway, this was the last frame before the pulse. Then the pulse itself was a whiteout because it was the sparking was so intense that it blotted out what you could see in my camera. And incidentally, it was doing 30 frames per second. And after 0.066 of a second, this was the situation. Now, I've replaced the actual system by a stylized box with an arrow on it, the arrow showing which direction it should be going. This was the situation, and I'll scroll through the subsequent frames, all separated by 0.033 of a second, and we'll see that it's dithering around the edge. What it actually hit there was the edge of the box, and if you imagine it started vertically, this is the second one after vertical, and running this in reverse with the arrow pointing in the direction that the force should go, then we see it going, and it twists a bit here because on the return journey, it was still a bit shook up by the collision with the edge of the box. And anyway, it goes up there, and if you do that back and forth, you see that it's actually going in an arc. And actually goes to an arc of about 45 degrees. And you can, either from the video or from my notes at the time, I noted it was 7 centimeters of wire suspending the coil. You can see that there's to the center of mass of the coil, because the height of the coil was 6 centimeters, so the distance into the center of mass was 3 centimeters. You add that to 7 centimeters and you get 10. So 10 centimeters implied that over this 45-degree movement of the coil, remember this is all within 0.066 of a second. So this is an extraordinary velocity. I'll go into that in the detailed calculations sheet later, which will prove that there were thousands of newtons in there. But what you see here is, again, that it goes forward and it collides with the side of the box and twists through almost 90 degrees as it essentially flattens up because of hitting the edge of the box. So all that happened, in this case, it happened through 10 times the speed on the way back, 10 times slower on the way back. It was going through 10 frames. 5 of the frames were in motion, and 5 of the frames were hitting against the edge. So that's why I say that for one of the time steps, 0.033, the system was going through 7 centimeters, because that's, if you're going to 45 degrees with 10 centimeters, that's pi over 4 multiplied by 10 centimeters gives you about 7 centimeters. Work it out for yourself there. And I've done it numerous times, so I know that that was exactly the setup. And I'll go on to the sorry, gone too far here. Okay, so I'm going down now to show the actual device. Well, this wasn't the actual device. This one was one giving 10 kiloamps, but the one we were using produced a maximum of 30 kiloamps, 30,000 amps. But we were told that due to the impedance in our coil, we would only see at most 10 kiloamps. And we'll see if that's the case in the calculation sheet. And you can see what wonderful devices these are. You have the electrodes on the right and the left of these lights. The green light tells you that the capacitors are all charged up, ready for the pulse. And then you pulse it and the red light flashes and the pulse goes through. And anyway, onto the calculation sheet. As I say, I had about 5 centimeters in point. This is a conservative estimate in 0.033. For all I know, it was 10 centimeters in one time step. That's the difficulty with having a low resolution. If I ever do a proper finance test of this, we will both buy the surge current generator, which costs about 20,000 euros, and also have a high-speed camera to really do proper framing of the whole thing at multiple frames per second, much more than 30. And anyway, this is what we have to work with. So a conservative estimate is 5 centimeters in 33 milliseconds. And that gives a velocity of 1.52, because that's 0.05 divided by 0.033. You can see that that's the equivalent of 5 divided by 3.3, which is 1.52. And this was all imparted in an acceleration time of the pulse, 20 microseconds. So to do the calculation of what the acceleration had to be, the velocity, plugging in the velocity in the standard mechanics equation, velocity equals acceleration by time, is velocity from above 1.52 equals acceleration by the 10 to the minus 2 by 10 to the minus 5 equals, so that implies that the acceleration is 76 kilometers per second squared. An absurd acceleration, but it shows what an intense acceleration you undergo here. And to see if this was due to the Lorentz force, we first of all get the amp turns, Ni. There was 20 turns in the coil, so that was 20 I. And to get the Lorentz force, that's the amp turns squared multiplied by 10 to the minus 7. And because 20 squared is 400, 400 by 10 to the minus 7 is 4 by 10 to the minus 5 times I squared. And if we set this current equal to the mass by the acceleration above and plugging in the 0.7 by 10 to the 5 meters per second, we get 0.76 by 10 to the 4 multiplying by 0.1, the mass of the coil. And then we get I squared equals 0.19 times 10 to the 9, giving current equals to almost 14 kiloamps, which was a bit more than was estimated, about half of what was available, the maximum 30 kiloamps. And by the way, this proves that the force relationship was the more optimistic one of 10 to the minus 7 and not 10 to the minus 9 of the three-dimensional sims, because for the 10 to the minus 9, it would have had to be 100 or 10 times more current than the 14, which would have been 140 kiloamps, which is beyond the way beyond the specification of the pulse generator, of the surge pulse generator. This is just a bit more than the estimated, as I point out. And here I do the calculation for the Earth's magnetic field to show that it only produces 5.52 newtons, giving a velocity of only 1.1 millimeters per second. Over the 0.066 seconds of the 2 frames of the video, this would only have given a movement of 0.073 millimeters. This is why I say that the Earth's magnetic field is totally wiped out here. So that's why you don't have to correct for the Earth's magnetic field here, and why in my improved system, I'm going to use this the forward system, where I move normal to the plane of the coil, because the Earth's field is no longer a problem. Anyway, looking at the performance compared to some other thrusters, you can see that the normal Lorentz system is about equal to the Newton to watt efficiency of ion propulsion or DC jet engine, etc., or even similar to the rocket. But it produces, the difference is it produces many newtons for some kilowatts. However, in the last 2 years, although most of this work was done 10 years ago, I've been thinking on and off about it. I had many different ideas about how to improve the system. And in the 2 years, I made a breakthrough, and I found a system which would give 1 Newton per watt. Again, this was going normal to the plane of the coil, would give 1 Newton per watt. And this was, with my simulations, you could make a very heavy system of about 50 kilograms, but the beauty of it is it produces thousands of newtons at room temperature without overheating the coil. And so you get liftoff of this coil, a very impressive demonstration. However, the construction is quite expensive. For a prototype, you would need about 10,000 euros, I would say, at least. Anyway, I've set up 5 different replications of the system. And the first one was this low current case with using the car battery as power source. Again, I have all these steps that I went through, which aligning with the horizontal component of the Earth's magnetic field, with the vertical component of the Earth's magnetic field. And also, at the beginning, you have to have it completely still. So sometimes you have to go away for a few minutes and let the coils be settled down from random vibrations, etc. And then you're sure that it's completely still and you've adjusted it for the horizontal and vertical components. Then you can pulse it and you know that the lateral movement is due to your Lorentz force. However, as I say, the surge current generator is much more satisfying. So if you have funding of 10,000 to 20,000 euros, you can buy one of these, or you could borrow one. There are cases, there are some companies which lease these out. I don't know if Hilo GmbH in Karlsruhe allows that, but I did see somewhere in the last few years that one of the companies allows you to hire these surge current generators, and you can then do an incontrovertible test. You don't need to use the sample box anymore, because the only reason they had the sample box was in case the whole system exploded with dangerous metal flying everywhere. We showed that wasn't the case, although the coil was a bit dented by its collision. Incidentally, another proof that it had collided with the side of the coil, it was scrunched up a bit in the plane of the coil, as it were, a bit like a car banged up after a crash test. And but with the if you eliminate the sample box, you could, if you had a loan of the surge current generator on its own, you could simply again have the system whatever, a meter above the actual generator, but free to move in 360 degrees, and with a high resolution camera that can handle high luminosities. And if you have that, or if you have, say, two cameras, one for high luminosity and one for low luminosity, then you can combine them to get a complete picture of what happened in the first few milliseconds of that pulse, after the pulse, or even during the pulse. So anyway, in the third replication, you're not yet at superconducting, because the problem with superconductors, I find, is they're too sensitive. I was inquiring with Sigma Phi in the Normandy, a company which deals with superconductors, and they mentioned all these caveats of quench and homogeneity of field, and the shape of the coil must be completely circular. You have to use a completely circular coil and put on attachments that are very smooth and don't change the flux dramatically or catastrophically, because that will all lead to shuddering and quench and all that. Anyway, what we use here instead is the next best thing, which is pure copper wire, 99.9999%. In the business, they talk about 5R or 4R copper. There's even 5R. That means the number of decimal places after the point. If it's 0.99999, then it's 5R. And it gets more expensive the more R's you have in it. And the 99.9999% copper wires already, you will have to spend a few €100 anyway on the actual coil. And then you have to pay for the liquid helium, etc., to cool it. And so the whole thing costs probably a total of 1,000 to do this test. And also you have to have a very thick coil to ensure that even at normal room temperatures, you get 0.1 newtons at least, because you're going to get 1,000 times more force from this system. So that would mean that 0.1 newtons becomes 100 newtons, which would be very good, a very good test. And you could do this not only for a few milliseconds, but for continually. So you could move a wagon around, or you could have anti-gravity. You could have the thing move up in the air for about whatever many seconds, or even a minute, maybe, depending on the cooling. And replication 4 is to use this proprietary improvement to the basic system. And that gets a very efficient system, but it's very difficult to make the prototype, and involves some expert coil winding, etc., and expert deposition of these devices, etc. And the whole system would then be cost at least 10,000, maybe even 20,000. But the advantage would be that at room temperatures, it will give 1 Newton per watt and continuously without overheating the coil. And you can get even temporarily 100,000 Newtons or something from a high current pulse. But even at a relatively low current of 1 or 2 amps in the coil, you would get this thousands of Newtons. And if you're using pure copper wire at cryogenic temperatures, you actually now get 1 kilonewton per watt, which amplifies the system doubly. So you have already, you've augmented it by this special coil up to 1 Newton per watt. By the way, the normal one gives 1 kilowatt per Newton, 1 Newton per kilowatt, which is not much better than some of the ion thrusters, etc., except you're not using any ions. But if you use the basic setup for this improved coil, then you would get this amazing 1 Newton per watt and 1 kilonewton per 1 kilowatt. And going to the cryogenics, it just shoots it up to the ceiling. You get 1 kilonewton per watt or 1 meganewton per kilowatt, which is extraordinary. And application 5 is to use a superconducting coil. This is the most uncertain one of them all, I find. You would have to spend about 100,000 euros on the whole thing. And you have to be very careful to avoid quench. The quench is when you fall out of the superconducting system and it has to go into the pure copper surroundings, because note that all these superconductors are wrapped in pure copper, in 5R copper, because only that can take up the slack if the thing jumps out of superconducting mode and during quench. So, but if you can avoid quench, then you can get, for these superconductors, you can get 1 mega amp into a square centimeter or 4 square centimeters, let's say, to be safe, because I think it's an absolute world record getting 1 mega amp into a square centimeter cross section. So let's be conservative and say 4 centimeters, then you have a fairly bulky superconducting coil and with lots of liquid helium around it or whatever, or if you're at high temperature superconductors, you use lower coolers, liquid nitrogen, etc. But the advantage of this is that a mega amp will give you 10 to the 5 newtons, almost as many newtons as amps. And but you would have to have massive mechanical constraints to contain this enormous force. This would be, this is equivalent to the launching of a rocket. But in fact, to launch a Lorentz rocket, you don't need hundreds of thousands of newtons. Tens of thousands of newtons from my normal system would be enough. You would just have 4 of my souped up coils in the 4 corners of a capsule, let's say. It would be like you're launching in the capsule without the rocket. You just have the basic capsule and you go forward up at 2g in the Earth's gravity, just enough to overcome the Earth's gravity plus one more on top of it. And when you go out of the Earth field, you go back to 1g, a comfortable thing. So your bones don't decay in the long journey to Mars of only a few days. Because even with the flip around, at halfway point, you flip around and you're braking for half the time to Mars. So you accelerate half the time and brake half the time. And that only takes a few days, even at a fairly unfavorable position of Mars. So you can even be at Mars in a few days when it's almost on the other side of the sun, maybe a week or so. But when it's in a favorable position, you can reach it in just over a day. And anyway, also inhomogeneities in the system may mean it can't work. So only time will tell. I see I'm reaching the end of the time, but luckily I've hit the summary slide. So I know it wasn't very dramatic visually, the presentation, but I hope the message was dramatic. We have a new propulsion system, and this has the potential to revolutionize not only space travel, but also terrestrial travel. I mean, we're talking here about a technology that could end global warming, because you would have electro cars going for thousands of kilometers without servicing. They wouldn't even need petrol or recharging from one of these recharging stations. They would all be superfluous as well. And also all windmills and solar panels would be superfluous, because you could just power generate ad nauseum from putting two of these units on a generator, on arms attached to a generator. Small ones of these could power a house, and big ones could power a city and whatever. So this is one reason why physicists have always resisted. I'm a physicist myself, so I know what I'm talking about. And the majority of physicists will resist this tooth and claw, because they know that if Newton's third law falls wounded to the floor, it won't be broken, because my nonlinear stuff only bends Newton's law to 90 degrees, as it were. But even though Newton's law escapes with a bandage or whatever, the first law of thermodynamics is in the bin, because you can generate this energy. And the ideal platform would be, you would have two of the coils under the floor generating the energy for all, including themselves, and the other coils, which would be lifting the whole demo platform off the ground. And you would have a great anti-gravity demo. Anyway, all this stuff takes a lot of funding, so I would invite any entrepreneurs out there to join me in funding of this business. Thank you. Oops. That's it.
Wonderful. Well, Hugh, thank you, sir. And let me do this. I'm gonna stop your screen share there. Okay. And I want to put this on gallery view. Everyone, please give a giant applause to Dr. Hugh Deasy. And let me see, I'll do a screenshot there.
Yeah.
Yeah, no, sir, I cannot thank you enough for that presentation.